Okay,
Wonderful. Then let me welcome you everybody again. So we are now ready to start. And I will like to hand over to Mr. Lamacchia, who will introduce himself a little bit and then start with the presentation. Have a wonderful day.
Perfect. Thank you very much, Rod. Thank you. Thank you and welcome everyone to our webinar. My name is Martino Lamacchia. I'm Marketing Manager for Composites at Olin Epoxy for Europe, Middle East, Africa, and India. And today, together with my colleague Leif Meyer, we'll present our first webinar on epoxy filament mining. So next slide, thanks. Before deep diving into the topic, allow me to spend really 5 minutes at introducing Olin Epoxy for those of you, well, Olin actually, for those of you who didn't know it. So Olin, American company founded in 1892. Our headquarters is in Clayton, Missouri, not far from St. Louis. Our turnover in 21 has been around $9 billion. We are about 8,000 people, and we are listed on the stock exchange since a few years, actually. Now, I will definitely not bore you with the history, with the full history of Olin, but I would just like to mention 3 facts about our history that are relevant to our discussions today. Well, first of all, 1892, 2 companies were born in the US, Olin Industries, an ammunition producer, and the Matthiason Chemical Company, the first company in the US to make chlorine out of salt electrolysis. So chlorine is really in the soul of these companies since a few years. Then in the 50s, these 2 companies merged together, originating a diversified group active on chemicals and ammunition. And we are still today that kind of company. And then third fact I wanna mention, 2015, transformative milestone for Olin that in that year acquired from the Dow Chemical Company, the US chloralkali business, the global chlorinated organics business, and importantly for our talks today, the global epoxy business. And thanks to this move, Olin became the #1 global producer of chloralkali products, the #1 global producer of epoxy materials, inheriting this position from the Dow Chemical Company and bringing it to the next level. So Olin today is organized in 3 businesses: Olin Chloralkali Products and Vinyls, world leader in chloralkali; Olin Epoxy, world leader in epoxy resins; and Winchester, that is our ammunition business, world leader in small to medium caliber ammunitions. Now, if you want to remember something about Olin Epoxy, the few next slides are the key. So first of all, what do we do? Well, we leverage epoxy properties like lightweight strength, corrosion protection, electrical insulation, chemical resistance to actually approach those markets where these properties are valuable, like composites, like coatings, electronics, civil engineering. So this in 30 seconds, what we do. Now, let me focus your attention on this slide that I think is really the key differentiator that explain what is the key differentiating aspect of Olin. I don't know how familiar you are with epoxy chemistry, but I mean, from a super high level, to make epoxy resin, you need 2 things. You need epichlorohydrin, you need bisphenol A. And now most epoxy resin producers run a non-back integrated model, right? Sourcing on the market epichlorohydrin, bisphenol A. Now, this model might have some advantages, maybe lean assets, but on the other hand, is presenting some question marks in terms of reliability of supply. So how to reliably find on the market the epichlorohydrin that is needed to make liquid epoxy resin, for example. Epichlorohydrin is a structurally short material, causing big headaches to those who have to source it externally, but also causing some question marks on how scalable a non-integrated epoxy supplier is. I mean, epoxy resins are linked with many applications that will require a growing amount of epoxy resin going forward, like wind power, like composites. So a non-integrated model poses some question marks in terms of how to find the epichlorohydrin that we needed to supply growing amounts of epoxy resins into the growing epoxy industry. Now, as you can see now from the slide, Olin model is completely different. It's a deeply back-integrated business. And here you see why Olin, a chlorine leader, has acquired from Dow a global epoxy business, right? So a huge consumer of chlorine. I mean, this very deeply back-integrated model sees Olin starting from digging our own brine mines to make our chlorine, then converting it to allyl chloride, to epichlorohydrin, and then to our resins that are then converted into many other systems and products. And in the next slides, you will see our composite systems that are an example of what we do and what we use our structure for at the end. So in composites, we make systems for several technologies, from pultrusion to infusion to hand layup, HPRTM, prepreg, and obviously filament winding. That is the topic of today. And when talking about our composite business, we like speaking about performance at scale, right? And we like that because, we think that our deep back integration is putting us in the right position to supply in the long term the big growing volumes that some of these high growth composites application will call for. And a very good example of these growing applications are actually composite pressure vessel. And we get now near to our topic, right? Because, I mean, composite pressure vessels, they are linked to some of the mega trends that are shaping our industry, right? Think, for example, at climate change, decarbonization, so the big need to reduce emissions from transportation. 12% of greenhouse gas emissions come from road transportation. And so we are seeing a big shift towards alternative fuels. One of these alternative fuels is electricity. This generates a big market for battery electric vehicles, but also generates a big market for fuel cell electric vehicles, also known as hydrogen vehicles, right? So forecasts show that by 2030, we're going to see between 2 million and 2.5 million fuel cell electric vehicles on the road, mostly medium to heavy duty vehicles, so trucks, commercial vehicles. And these vehicles, being electric, they will need to, drive far to be attractive. And to drive far, they will need to carry on board a lot of hydrogen. And to carry on board a lot of hydrogen, this hydrogen will need to be stored at very high pressures. And that's where composite tanks come into the picture. This will also generate demand for, let's call it hydrogen infrastructure, right? So how to bring hydrogen to the refilling station and how to store it in the refilling station. And again, composite pressure vessels are going to be part of the game. We see similar trends in CNG vehicle, where again, to maximize the range of these vehicles, we need to carry a lot of CNG at high pressure. And again, composite vessels are an answer for that. And in the next slide, we see also a big shift or a big interest in optimizing payload, right? Again, to reduce emissions for transportation and to optimize the productivity of transportation. And gas container lightweighting is one of the trends, which ultimately allows to transport more things per shipment. And you see this happening in LPG, in industrial gases in general, where composite tanks are gaining ground more and more. So high growth application that will require growing amount of epoxy resins, and where we think Olin back integration and scalability is a very compelling value proposition. Now, let's come to the topic of our presentation in the next slide, which is, what is the role of the matrix in composite pressure vessel, right? And I mean, this is actually a pretty wide kind of question, pretty general kind of question. Actually, a good next question to narrow it a bit could be what matters in pressure vessels, right? What are the requirements and what role can the matrix play within these requirements? So in the next slide, we have tried to narrow down the discussion here to one specific application that we think is a very good example of what is the epoxy role, right, in this whole thing. So we are mentioning hydrogen, in this case, hydrogen pressure vessels, and we use as an example this table that comes from the norm EC 406 that regulates type approval of composite vessels for hydrogen vehicles. And the table here that we are showing is listing the tests that a hydrogen vehicle needs to undergo in order to gain the type approval. Now, in the next slide, you will see, in our view, metrics is key in at least 50% of these tests. So, and we want to mention two examples of that. So in the next slide, we have listed these two examples that we want to show. And I mean, at the end, when you look at what are the CTQs, right? I mean, we don't have time to go deeply through all these tests. But I mean, if you do it and if you read what are the requirements, yeah, you will understand that resin CTQs that really make a difference are fatigue resistance, fracture toughness, that can really, you know, again, play a vital role in pass-fail of these tests. And we want to show you two examples of these. The first example we want to show is temperature cycle test. Here you see what happens to a clear cast of epoxy resin where a solid object has been put to facilitate the generation of cracking. So what happens to this clear cast when it's cycled between -20 and 80 degrees for 10 times? You see the difference between a toughened epoxy resin and a non-toughened epoxy resin. And I think the pictures are self-explanatory, right? So you see yeah, how the selection of the proper metrics can play a difference, for example, in a temperature cycle test. Let's now go to the next one, where you will see the second example we want to show, which is impact test. So when generating a specified impact in specified condition on an impact test that is needed to gain the type approval, you clearly see a correlation between the impact energy and the burst pressure of the tank. And a good question could be, why is that happening? Now, if you look at the pictures in the next slide, you will see that, I mean, a reason for this correlation is the delaminations and microcracking that are generated during an impact. And delamination, microcracking, these are deeply dependent from the metrics, the type of metrics that you are choosing. I mean, the key high-level concept we would like to transmit here is not every matrix is the same, not every epoxy is the same. Different grades for different applications and requirements. If you take a look to the next, to the graph in the next slide, you will see, for example, that between a toughened system and a standard epoxy system, you can have huge difference in burst pressure, for example. So on the left, a standard system used to make a test, to make a tank, you see the burst pressure before and after the impact test. On the right, toughened system, again, burst pressure before and after. You see that the Olin toughened epoxy system is showing a 24% improvement in burst pressure following the impact damage. And honestly, you also see a slight improvement also before the impact, right? Again, to emphasize how the choice of the epoxy matrix can play a difference in some of the key tests to gain the type approval of a tank. So in the next slide, we are showing a sort of challenge, right, to you guys. And the challenge is, if thanks to an enhanced resin, you can gain some extra performance, as you saw in the previous slide, for example. Yeah, why not thinking at optimizing the fiber content of that tank, bringing the performance back to the previous level, having saved some costly and short fibers. So this is a bit the challenge we wanna shoot with this presentation. And in the next slide, I'm trying to wrap up this first section, just saying, hey, when designing a tank, when maybe trying to optimize this tank and optimize the fiber content of a tank, I mean, don't think at epoxy resin, at the matrix, as a glue for the fibers, right? And here we come to our title. That's something more. The epoxy matrix and the right choice of the epoxy matrix can play a vital role in pass-failing at least 50% of the tests that are needed in a hydrogen homologation test. So we are here to support and are very happy to support anyone who needs in selecting the right system for the right application. However, this is not the end of the story, right? Because not only epoxy is a key in the mechanical performance, ultimately, of the composites here we are talking about in our tank, but it's also one of the most defining elements of the processing of this tank in a wet winding process. And so in the second part of the presentation, we want to drive you through this other important aspect and through the role of the matrix into the processing. So Leif, all yours.
Yes, this was a signal for me to unmute. So hello everyone, also from my side. And thanks Martino for the first part. So actually during the first part of this webinar, we have heard a lot about the important role that a toughened epoxy matrix system can play to fulfill requirements on the performance of tanks, in particular the certification requirements that have been mentioned and shown by Martino. But in the end, I mean, for us as a resin supplier, the certification requirements of a tank do not represent the full critical to quality parameters that we get from our customers typically, because in the end, first of all, a tank needs to be manufactured, and so the manufacturing process is also driving a lot of these challenging requirements. So toughening is an important thing, but toughening is not completely everything, because some typical toughening agents which are used for toughening of thermosets do have some impacts on other parameters as well. Yeah, usually you are targeting to increase the fracture toughness of a system in order to achieve a higher damage tolerance. But typically what could happen is, for example, a viscosity increase, for example, by fillers or rubbers. It could be changes in reactivities if you're using inorganic fillers that have particular surface chemistries. It can be tensile properties change in case soft particles or soft faces are used, and this can have impact on the overall composite properties. And last but not least, plasticizers, which can also be a method to achieve toughening, would have an impact on the glass transition temperature, and so finally on the service temperature of the tank. So in the end, we need to consider all these different parameters. Yeah, and like shown on the right side, we need to find the right balance between the performance-driven requirements and the manufacturing-driven requirements. In order to dive a little bit into this topic, we have prepared a second case study, and this would be the resin requirements for the classical wet winding process. So in this part, we are going to focus a lot on the manufacturing process. Yeah, and we have decided here to really focus on the let's say maybe most established but also most simple process, the very classical wet winding process. So if we look at this process, basically we are starting the process with a creel with the dry fibers on either bobbins or rolls in it. We have some fiber guiding, and then finally the first point where the resin comes into the game is the fiber impregnation, which, for example, can take place in a resin bath, which in the easiest form would be just an open bath, a reservoir filled with liquid resin. Then we are doing some handling of the impregnated rovings. We are winding it, typically around an inliner material, either made of metal or of polymers. Today we see polymers dominating the picture, in particular for gas storage. Once the winding step is completed, it's the tanks still with the liquid matrix are transferred into a two-step oven process. In the first step, usually the gelation or initial cure is the target, and then in the second step, it's the so-called post-curing. The step where the full degree of cure, final TG, and final mechanical properties are achieved. So overall, we see 4 to 5 or even 6 process steps, depending on how deep you dive in the different processes. And so overall, it looks a little bit too complex to directly guess on the processing or on the resin requirements based on this process. So basically, what we decided to do is to use a very, very simple engineering approach. First of all, cutting the process in small pieces. Secondly, eliminate what doesn't have an impact on what we want to talk about. And you can see we are eliminating the fiber handling and guiding. This is where the resin does not yet play an important role. And in the end, we are also simplifying here a little bit. So let's start to run through the process, starting with the fiber impregnation. So the purpose or key process requirement of the fiber impregnation is typically to provide a very good wetting of the fibers, to really cover all the fiber surfaces with epoxy resin, to have no air entrapments or other kinds of bubbles, which would be a deviation from the desired condition. And last but not least, we expect this also to run over a relatively long time in a kind of stable process without a lot of need to do corrections. Based on this, the key material requirements for this fiber impregnation step, first and most important is really for the viscosity to achieve this very good and excellent wetting, add a good and high line speed to achieve also productivity, is basically the viscosity needs to be low or even very low. It's really for the wetting. In particular for carbon fibers, the viscosity should be as low as possible. Looking at the pot life, in particular for the classical open bath should be as long as possible. Or let's put it a little bit different, as long as needed. I mean, if you have a process and you are able to run this process with a very small bath volume, you may be able to accept some compromises on pot life, but in general, what we still mostly see is relatively big resin bath volumes. So basically, you need this entire volume of the material not to react and to keep the pot life and workability over a very long time. So reactivity should be low or even latent. And of course, you also don't want to have any reactions that are causing exotherms at this step of the time. So we're going to use more or less the same scheme for evaluation for all the different process steps. So let's look to the second step, the winding process itself. Basically, what you want to see here is a good fiber placement, a sufficient tech of the material. You also don't want to see resin dripping due to 2 reasons. First of all, you're paying for the material. But secondly, of course, I mean, this would impose a lot of cleaning requirements to your manufacturing environment. So this needs or should be avoided or minimized as much as possible. You still want to see, you still do not want to see high exotherm behavior in this step. And this is in order to protect the liner material, which, as I mentioned, typically is a polymer material with a certain temperature stability. So you cannot afford to exceed the temperature stability of your material. And last but not least, also here you want to avoid air entrapments. So regarding the material requirements, the viscosity could be higher compared to the bath step, to the impregnation step. So I would call it medium to high. For the pot life, in this step, you do not have specific requirements anymore. The winding itself is relatively fast, so you don't need a long pot life in this step. Regarding reactivity, it's more or less the same. And regarding exotherm, still you don't want to exceed the stability of your inliner material. So during gelation, the material is let's call it transitioning from the liquid state into the solid state, or first into the gel state. And this is what we call the so-called vitrification of the material. So yeah, the material gets hard but not yet fully cured, and viscosity moves from high over gelation basically to infinite. The key requirement in this process is still avoid high exotherm. I mean, this is where a lot of the chemical reaction of the cross-linking of the epoxy takes place. So this is really one of the critical steps where you need to make sure to protect your liner material. You still want not to see any resin dripping, and you want to be this viscosity build or vitrification as fast as possible. Yeah, you can see from this fast viscosity build and avoidance of exotherm, there could be a bit of conflict. So viscosity in this step should be high. Pot life can be short, reactivity can be high, but this still at a low to moderate exotherm. So again, looks a little bit challenging to combine all these different requirements. The final process step is the so-called post-curing. So building the final degree of cure, achieving the final TG and also the final mechanical properties. Ideally, you want to have this step as short as possible. I mean, this is determining your cycle time in manufacturing a lot, but still you need to make sure that you need to protect your liner material. So overall, the requirements in this step are a bit limited. You don't care about viscosity anymore. You don't care about pot life anymore. You're just interested in a high reactivity at a manageable exotherm level. All right, so these are basically the singular steps. So let's try to move into the direction to recombine this into the entire process. And in the first step, let's look at the viscosity profile. Basically, what we learned in the fiber impregnation, you're targeting viscosity as low as possible. However, then you expect a very steep increase, or you could expect a steep increase towards the winding process, and then in the end, upon gelation and cure, you expect it to be on the pretty high side. So overall, this viscosity increase over the process makes sense. I mean, chemically, you're increasing the network density, the degree of cure over the process steps. So in general, it makes sense. However, there are still some conflicts, and this is, for example, in the resin bath, you want to have low reactivity, low exotherm, long pot life, low viscosity, and at the same time, right in the next step, which is just a couple of seconds away in the process, you expect a very steep viscosity increase, and all this also at low exotherm. So there's a little bit of conflicting parameters in this step, and in the end, these conflicts need to be managed by choosing a proper temperature profile during the individual process steps. And I'll come back to the temperature profile on one of the next slides. If we look at the other parameters, at pot life, reactivity, and exotherm, I combined all of these in one graph because actually they are kind of dependent from each other. Yeah, it's pot life requires low reactivity in the liquid phase. Exotherm requires low reactivity in the entire process. So it looks overall a bit more complicated. And I would say overall, the key determining parameter for type 4 pressure vessels is definitely to manage the exotherm over the entire process. Yeah, the critical point is really to keep thermal damage away from the inliner material. Overall, it still makes kind of sense. Reactivity low in the beginning and increasing over time. So this is something that can be managed. So the process requires low reactivity during wetting, high reactivity in the final cure, and in the end, very high reactivity in the post cure, which is not easy to achieve chemically. There are methods to use, for example, some catalysts But this again needs to be balanced with the other parameters. And this is a little bit key of my statement here. There are always potential conflicts and limitations between reactivity, viscosity, and exotherm. And in the end, this needs to be adapted via the temperature profile. At the same point of time, seeing this conflicting and complex profile of requirements, we can already assume at this point of time that there may not be the one-fits-all solution for a good epoxy filament winding system, and that depending on the process and different other parameters, a certain portfolio and adjustment is needed. So looking at the temperature profile, typically what is used is that in the resin bath, let's say the typical working temperatures are ranging from room temperature up to 50 degrees C. The upper limit limited a little bit by the pot life of the material, so of the resin hardener chemistry. And basically the purpose to increase a little bit over room temperature here is to achieve a further reduction of viscosity, to even further improve the wetting process. For the winding itself, typically we see this being done at room temperature. Would be also possible to have slightly elevated temperature, but the critical point is here to avoid the exotherm. So basically, this is why typically this is a little bit in the conservative temperature field. Then the gelation is typically done between, basically for some of our resins, it could be done at room temperature, but typically what we see is roughly between 40 and 90 degrees C. The limitation is here the exotherm in relation to the liner material. And for the post-cure, in the end, we see ranges from 75 to up to 150 degrees C for high TG systems. Again, with the limitation upwards being the liner material at this point of time. All right, if we combine this back into a high-level material specification, my clear statement is the good fiber wetting is a key requirement, and this requires very low viscosity during the impregnation stage, whatever resin you use. This is a key requirement, because if you have flaws in impregnation here, if you have air entrapments here at this point, you will carry them on through the process, so you will have an impact on the quality of your pressure vessel. This can be supported by carefully increasing temperature of the resin bath. And this is where we can help you with reactivity data of our resins to find the right adjustments. In the end, for the wet winding process, low reactivity or long pot life in the resin bath is another important requirement in order to avoid early gelation, which would cause the need to have regular clean out of the entire resin bath, and so limiting the productivity and causing waste at the same point of time. So long pot life is the second important thing. And then basically the higher viscosity during winding, this can be a beneficial aspect. It can be managed by running the temperature profile. It can also be managed by choosing the proper resin hardener combination. And in the end, in the final steps, in the gelation and post-cure, it's everything about reactivity. How fast do you build up the cross-link density, the molecular network, at which temperature is required to get there. And this is also where we have a range of different resins and hardeners to choose from, and where we can support to find the right balance. So overall, it's coming back a little bit to a picture that I've been showing in the beginning with the balance. We have some conflicting parameters, and this is reactivity, viscosity, and exotherm. So regarding viscosity, you want to have it low, but you want to see a fast increase without exotherm. So this is chemically and physically a conflict in itself. Regarding exotherm, you want to see a low exotherm, but at the same time, you want to have a fast cure speed, which is again kind of a chemical and physical limitation that we have here. And regarding reactivity, you want to have a low reactivity in the beginning in the bath, in the liquid phase, but as much reactivity as possible in the solid state to keep your post-curing cycle as short as possible. So this again is representing a limitation. So the learnings from the process study, one of the conclusions that we have is very clear and very obvious for filament winding of pressure vessel. There is not a one-fits-all solution from a processing perspective, from a manufacturing perspective. And for all the different manufacturing details and also details of the vessels, it's always about balancing the conflicting parameters between productivity and quality of the filament winding process. So the final specification of the material and the choice of material will always depend on details of the manufacturing process. Can you handle a small bath volume so that you are able to process higher reactive systems? Or do you need to have really a full latent systems so that you can run a very big bath? It's about the size and the wall thickness of the vessels to be produced. Yeah, a very thick wall thickness is always more prone to have effects of higher exotherm. The fiber type is basically critical. It's the wetting behavior. The liner material is critical because it's limiting your maximum allowable temperature during the tank. Then, of course, the final tank requirements, desired line speed, so productivity, and so on and so on. So overall, we have a lot of parameters that we need to balance and where we need to find the right way. So basically at this point, I'm coming back to the initial topic that Martino often opened, and this is the topic about toughening. So we learned that toughening is a key requirement to achieve good tank performance and to have safe and reliable conditions to fulfill the certifications. We learned that a lot of toughening agents are impacting parameters that could have a negative impact later on for our manufacturing process, for the processing of the tanks. And so basically the question is, what can we do about it to combine this toughening technology with the manufacturing requirements? Basically what we have is our own toughening technology, which is based on basically on a liquid modification of our epoxy resin. So basically, in simple words, we are using a liquid block copolymer technology, and you can see it in the image on the upper left. This molecule has a side that likes epoxy and another side that doesn't like epoxy. So, and in the liquid state, this is fully mixed into the epoxy. In the liquid state, there's no separation or whatever. And you don't have a negative impact on the viscosity of the system. So our toughening modified resin or toughening modified hardeners are showing exactly the same viscosities as the non-toughened ones. So what is happening upon cure of the epoxy system is that these epoxyphilic and epoxyphobic sites start to order themselves. And upon curing, you have a so-called safe assembly structure. So those liquid block copolymers are forming kind of particles inside the matrix, and these particles they are responsible for the toughening effect. So it's really low viscosity toughening approach. So creating the benefit of toughening without negatively impacting the manufacturing requirements. And so in the end, this technology enables us to create a very good balance between the ease of processing and the performance of the tank with regards to certification, with regards to reliability and safety of the tanks. So this technology is available in a range of filament winding systems that I'm going to show you in a minute, and this is a little bit coming back to what I mentioned. From a processing perspective, there is not the one fits all. So we have a full portfolio of filament winding resins and hardeners. Most important, we have a range of different viscosities available. to match parameters like the fiber wetting, like fiber slipping, and also TG. We have also different grades here. We have two different hardener chemistries available in our portfolio. On one hand, the amine hardeners, which have benefits with regards to curing at lower temperatures, and the anhydride hardeners, which have their benefits in being very low reactive at room temperature, even kind of latent. And last but not least, we have the toughening technology available for both of these cure chemistries. So looking into our anhydride curing systems, we basically, we have kind of a base system, which is our Lightstone 2131H, the hardener, and the resin Lightstone 2130O. We have the Lightstone 2142, which is the hardener which would implement the toughening technology as described before. And then in two different steps, we have the ability to increase the viscosity if this is needed for the processing. Overall, a key benefit of our system is that typically we are supplying 2K systems. We have an additional catalyst, the Lightstone 200C, in our portfolio, which can be used to adjust the reactivity. But this is not necessarily needed. So all our systems can be run and can be operated as a two-component systems without the need to have additional catalyst mixer. For the amine, our portfolio looks similar. Again, we have kind of a base system, which is always a good starting point if somebody starts working on filament winding. Basically, then we have a hardener, which is, again, implementing the toughening technology. We have two different hardeners, which are adjusting the reactivity, so the ability to adjust the formulation towards longer pot life. And in essence, I mean, these two hardeners, they can be processed from an open bath, I would say almost similar to anhydrides. Not exactly with the same latency, but almost similar. And again, we have two different resins to move either to higher or to lower viscosity. So the overall value proposition, again, here we are talking about 2K systems. We have toughening available. In general, the amine systems have very good mechanical performance. We can adjust the viscosities and we can adjust the reactivity. So basically everything that is needed to match all these challenging processing requirements that we have discussed before. All right, with this, I'm coming almost to the end of the presentation with some conclusions. So basically, the key learning from the first part is basically the certification of the hydrogen pressure vessels and also other pressure vessels is following very stringent certification requirements. And those requirements are or can be influenced and driven a lot by choosing the right resin, and those can be addressed by our formulated epoxy filament winding systems from Olin. Toughening is a key parameter for a lot of these requirements. And the second set of requirements is determined by the manufacturing process. And this is really where low viscosity is a key benefit to achieve a good quality and stable and reliable wetting of the fibers. But on the other hand, we have seen that the full resin specification depends on a lot of details of the design and processing requirements, basically where you always need to find this balance between the different requirements. So we are offering a range of filament winding system, including toughening, including different cure chemistries and cure kinetics, and with flexibility on viscosity. And we are here and there to help you choosing the right system for your process and your tank project, basically from this portfolio. With this, I'm at the end of our presentation. Thanks a lot for your attention. And yeah, I think we are ready to take questions.